Find the two complex numbers a plus bi such that a plus bi squared equals minus 3 plus 4i. There are two ways to do this. The first way that I will do it is to expand this thing out, write it as a single complex number, get its real part, get its imaginary part, and compare it to the real and imaginary parts of the complex number on the right hand side. So if we square this out, we get a squared plus 2abi plus b squared I squared, and that must equal minus 3 plus 4i. So we square the first term, multiply the first term by the second term and double, then square the second term. So that's just squaring a binomial. That means squaring an expression that has two terms. Now, I squared is minus 1. So we can replace this with minus 1. So we have minus 1 times b squared. That gives us minus b squared. So I'll put all the terms that do not involve I together at the start here. Those terms are a squared minus b squared. The term that involves I is 2abi. And on the right hand side we have minus 3 plus 4i. Now, we have a single complex number on the left hand side. Its real part is a squared minus b squared. Its real part is made up of these two terms. So this part does not involve I, and it must equal the real part on the right hand side. That's the only way that two complex numbers can equal each other. Also, the imaginary parts must equal each other. So we must have that the coefficient of I, which is 2ab on the left hand side, equals the coefficient of I on the right hand side, which is plus 4. So we get two equations out of this. We have two nonlinear equations in two unknowns. The easiest way to solve between these two nonlinear equations is to make A the subject of the second equation. Of course, we could have made B the subject, it doesn't matter. But I've made A the subject, so A is 4 divided by 2B, which is 2 over B. Just divide above and below by 2. The next thing you should do is substitute 2 over B in for A in the first equation. So we get 2 over B squared minus b squared equals minus 3. So that gives us 4 over b squared minus b squared equals minus 3. And to get all of this into a straight line, we multiply everything by b squared to cancel the b squared in this denominator. So I'll just continue on up here. If we do that, we get 4 minus b squared times b squared, which is b to the power of 4, equals minus 3b squared. Now this is a quartic equation. Because, well, the highest power is 4, but we can transform it into a quadratic equation by making the following substitution. What we do is we let b squared be replaced by something, well, here I would call it x. So then this will transform into a quadratic. So if x equals b squared, we get 4 minus b to the power of 4. Well, what is b to the power of 4? Well, that has to be x squared. Because if you square x, well, you're squaring b squared. That's b to the power of 2 times 2, which is b to the power of 4. And on the right hand side we have minus 3 times b squared, which is x. Now, we get this into the standard form of a quadratic equation. That means we want 0 on one side. If we do that, we get x squared minus 3x minus 4 equals 0. We solve this quadratic equation. It does have factors. The factors of minus 4 are minus 4 times plus 1. Those are the correct factors of this quadratic equation. The product of these two gives you 0. The only way that can happen is if either of them is 0. So if x minus 4 is 0, that leads us to x equals 4. If x plus 1 is 0, we get x equals minus 1. Now we know that x is equal to b squared, so now we can solve for b. So we have that b squared equals 4, which leads to two values of b, plus 2 or minus 2. Now, we also have that b squared equals minus 1. So we have two values for b here. We have the positive square root of minus 1 or the negative square root of minus 1. Well, the square root of minus 1 is either I or minus I. You know, we know that I squared is minus 1, but minus I squared is also minus 1 actually. We take minus I and square it, we get minus 1. Minus I squared is just the same as plus I squared, which is minus 1. Now let's look at corresponding values of a, we know that a is equal to 2 divided by b. So when b is plus 2, we have that a is 2 divided by plus 2, which is plus 1. If b is minus 2, we have a equals plus 2 divided by minus 2, which is minus 1. What about if b equals I? Well, if b equals I, we have 2 divided by I. Or if b is minus I, we have 2 divided by minus I. Now 2 divided by I is actually minus 2i. 2 divided by minus I is actually 2i. It's easy to check that. If you have 2 divided by I, just multiply above and below by I. So you get 2i on top, and you get I squared underneath, which is minus 1. 2i divided by minus 1 is minus 2i. Similarly, if we have 2 over minus I, then if we multiply above and below by I, we get plus 1 underneath. We get 2i divided by plus 1, which is 2i. As a matter of fact, 1 over I is minus I. Now, we're told here that there are two complex numbers, a plus bi, that satisfy this equation. Well, we seem to have 4 pairs of values. Let's see what this could mean. Let's look at this pair here. When b is plus 2, a is plus 1. So we get a plus bi equals 1 plus 2i. So that's one solution. We also have that if b is minus 2, a is minus 1. So here's another possibility. A is minus 1. A is minus 1, b is minus 2. Now it's no surprise here that this complex number is got by getting the negative of this complex number. Because when we square both of these, we'll get the same answer. Because this complex number here can be written minus 1 times 1 plus 2i. And if we square this, we're squaring this minus 1, which becomes plus 1. So really we're just squaring 1 plus 2i, which should give us minus 3 plus 4i. So we found the two complex numbers a plus bi. However, we've got other pairs here. Let's see what happens if we work with these. When b is equal to I, we have that a is equal to minus 2i. So a is minus 2i. B is I, so we've plus I times I. What's that? Well, that's minus 2i plus I squared, but I squared is minus 1. You see, we've just got back this one by using this pair. And what about the other pair? When a is 2i, b is minus I. So that's a. B is minus I. So we've plus minus I times I. Well, that's 2i minus I squared. That's minus minus 1, or plus 1. So we get 1 plus 2i. So we have just got the same as here. So there are only two complex numbers that satisfy a plus bi squared equals minus 3 plus 4i. So we could have ignored complex values for b. Let's just do a quick check. All we have to do is take one of these and square them. 1 plus 2i squared. We square the first term, that's 1. Multiply first by the second and double, that gives us 4i. Square the second term, we get plus 2i squared, which is minus 2. So this gives us, 2i squared is, 2i times 2i is 4i squared, which is minus 4. So we get 1 minus 4, which is minus 3, and then we have plus 4i. So it does check out. And of course, if we square minus 1 minus 2i, we'll get the same thing. Because that's just, as I've explained already, we can write it like this. So we take minus 1 and square it, that's plus 1. And then we just have to square the 1 plus 2i squared. And of course we get minus 3 plus 4i. Here's another method for doing this. Since a plus bi squared equals minus 3 plus 4i, we can write a plus bi as minus 3 plus 4i to the power of a half. So all you do is you just put both sides of this thing, of this here, to the power of a half. So we have a plus bi to the power of 2 to the power of a half. We multiply these powers. 2 times a half is 1. So we just get a plus bi. And that's equal to minus 3 plus 4i to the power of a half. Or you can think of getting the square root of minus 3 plus 4i. Now, what I'm going to do is write minus 3 plus 4i in polar form and use de Moivre's theorem. So to do that, we need to plot the complex number minus 3 plus 4i. It's in this quadrant here. And get r and theta. R is the modulus of the complex number. So to get the modulus, we get the square root of the real part squared plus the imaginary part squared. That's going to be root 9 plus 16, or root 25, which is 5, so r is 5. We also need theta. Theta is measured anti-clockwise from the positive real axis to the line joining the complex number to the origin. Now to find theta, we can start by finding this acute angle A. The side opposite A in this right angled triangle is 4 units long. The side adjacent to A is 3 units long. So tan of A is 4 over 3, or A equals inverse tan of 4 thirds, which is 53.13 degrees. So that means that theta is got by taking 53.13 from 180. So to 2 decimal places, theta is 126.87 degrees. So now we can write minus 3 plus 4i in polar form. So we can write it in the form r cos theta plus I sin theta, where r is 5 and theta is 126.87. And you can check this. If you multiply 5 by the cos of 126.87, you should get minus 3. If you multiply 5 by the sine of 126.87, you should get plus 4, or close enough to it, allowing for rounding. So now we want to put this number to the power of a half. So we put 5 to the power of a half, and we put the rest of this complex number to the power of a half, and we use de Moivre's theorem. So we have 5 to the power of a half into cos of a half multiplied by 126.87. So a half of 126.87 is 63.43. If we multiply 5 to the power of a half by the cos of 63.43, we get 1. 5 to the power of a half times the sine of 63.43 gives plus 2. So here's one solution. Now, we don't necessarily have to go into general polar form to get other values. We know that this is multi-valued, but it has just 2 values because the denominator of the power is 2, as I explained in earlier videos. This denominator gives the number, or the maximum number of distinct values that minus 3 plus 4i to the power of a half can take. The reason why we don't have to go into general polar form is because we're essentially getting the square root of this number, and we know that the square root of a number could be positive or negative. Like we know that the square root of 16 is either plus 4 or minus 4. So we have a similar notion here where we're getting the square root of minus 3 plus 4i. It could either be, if you like, positive, the plus 1 plus 2i, or minus 1 plus 2i, because we know that if we square this, we get minus 3 plus 4i. But if we square this, we also get minus 3 plus 4i, because if we square this minus 1 that's in front, we just get plus 1. So this other complex number is minus 1 minus 2i. So we have 1 plus 2i, or minus 1 minus 2i, as you saw before. Now we want to solve this quadratic equation. Now, it is actually a quadratic equation. It has complex coefficients. A is the coefficient of x squared, which is 1. B is the coefficient of x, which is plus 1. C is the constant term. That's the term that does not involve x. That's a complex number. It's 1 minus I. Well, actually, all real numbers are complex numbers. But 1 minus I is not a real number. So we use our formula for solving a quadratic equation. This formula is perfectly valid. It doesn't matter whether the coefficients are real numbers or not. So we just plug everything into this. So we plug 1 in for b, we plug 1 in for a, we plug 1 minus I in for c. Then we take care of what's inside the square root sign. So what we have inside the square root sign is 1 minus 4 plus 4i. That's minus 3 plus 4i. So we have to get the square root of minus 3 plus 4i. But that's something we've already done. We did that in part 1. The square root of minus 3 plus 4i is 1 plus 2i. Or if you like, we could put minus 1 minus 2i in here. It doesn't matter. The plus or minus will take care of the two possible values for the square root of minus 3 plus 4i. So the two possible values are plus or minus 1 plus 2i. So if we were to plug minus 1 minus 2i in here, the plus or minus would still give us the two different values for this square root. If we take the plus sign here, we get minus 1 plus 2i. That leads to just 2i on top. 2i divided by 2 is I. If we take the minus sign here, we have minus 1 minus 2i. That's minus 2i divided by 2, which is minus 1 minus 1i. Notice that the solutions are not a conjugate pair. We only get a conjugate pair, we get conjugate pairs when the coefficients a, b, and c are real numbers. Then if we have complex solutions, they come in conjugate pairs. In other words, if one solution was, say, minus 1 minus I, then the other solution would be minus 1 plus I. That will happen if the coefficients are real numbers. But when the coefficients are not real numbers, see, c is a complex number, then in general we do not get conjugate pairs. We can check our answers by typing in our quadratic equation here. And here are the two solutions, minus 1 minus I and I.